Hello everyone, today is the class number 35. Class number 35 for EMFT. Okay. So today's topic will be classification of magnetic material. Right? Classification of magnetic material. Classification of magnetic material. Okay. Right. Depending upon the values of the magnetic susceptibility, that means depending upon psi m or the relative permeability, or you can say relative permeability, because we know the relation psi m equals to 1 minus mu r, right? So from this concept, depending upon this magnetization or psi m or the values of relative permeability, that is mu of r, the magnetic materials are broadly classified into three categories. Okay, so first one, right, paramagnetic material. Second one will be diamagnetic material. And third one will be ferromagnetic material. Okay, so you have to write one by one, and I also discuss one by one. Okay, so first one, paramagnetic material. So actually what the paramagnetic material does, right, in the absence under this heading, right, subheading, in the absence of any applied external magnetic field, the permanent magnetic dipoles in a field, in a paramagnetic material are randomly aligned and thus do not have any magnetism, and thus average magnetic field is also B0. That means for this case, I again repeat, in the absence of any applied external magnetic field, if there is no magnetic field is applied over this material, then the permanent magnetic dipoles in a field or in a paramagnetic material are randomly aligned. That is what? So random magnetic dipoles are randomly aligned. Okay. So this is the nature of the dipole, okay, for this paramagnetic material, and results the magnetism small m equals to 0. Okay, and also B, average magnetic field inside the material will be 0. Average magnetic field inside the material will be also 0. Okay. So next, right, for the paramagnetic material, mu of r will be greater than 1. So for paramagnetic material, mu of r greater than 1. So as the mu of r greater than 1, then that means this values of psi m will be less than 1, right? So these are the values for these paramagnetic materials. Okay. So what is the example of this paramagnetic material? Right, air, platinum, tungsten, potassium, aluminium, chromium, palladium, copper sulfate. These are etc. These are all the paramagnetic materials. Okay. Next, we will move into the diamagnetic material. So what is the diamagnetic material does? See, the diamagnetic material in the magnetic fields, right, in Okay, so paramagnetic material, you have to we also comment one statement for the paramagnetic material, right? Under the experience of any external magnetic field, under the experience, write this sentence also. Under the experience of any magnetic field, the materials are aligned. The materials are aligned for few cases. That means materials are aligned for few cases. That means M becomes, magnetization becomes not equals to 0, but very tends to equals to 0. M greater than 0, but tends to equals to 0. That means a small amount of magnetization will develop inside the material under the experience of an external magnetic field. Okay. So next I will move into the diamagnetic material, right? For diamagnetic material, absence or presence, in absence or presence of any external magnetic field, the material cannot be magnetized. That means this diamagnetic material never be magnetized. Okay, never be magnetized. Okay, that means M exactly equals to 0 under or without experience of any external magnetic field. That the results B equals to also 0, and mu of R, your mu of R is less than 1. Okay, mu of R is less than 1. That means psi of M less than 0. Okay, psi of M less than 0. Okay, actually it also be less than 0. Okay, so this is for diamagnetic material, right? The example of the diamagnetic materials are copper, gold, silver, lead, silicon, diamond, bismuth, antimony, mercury, tin, water, nitrogen, hydrogen. These are all the examples of your diamagnetic material which never be magnetized. Okay, which never be magnetized. Okay, so next, write ferromagnetic material. What is the ferromagnetic material? Right, in this type of materials there is a strong interaction between neighboring atomic dipole moments. There is a strong interaction between neighboring atomic dipole moments. Right, then write ferromagnetic materials are made up of small patches called magnetic domains. So they are made up of small patches called magnetic domain. Okay, and which are aligned in a certain manner with or without experiencing any external magnetic field, with or without experiencing any external magnetic field. That means they are aligned in a certain way. Okay, so that means it will produce north pole and south pole inherently. Some of little amount of small north pole and the south pole are produced by this material. Okay, so here, right, here M will not equals to 0 and M is greater than 0. Okay, M is greater than 0. That means B is also greater than 0, and mu of R, relative permeability. So whatever the value relative permeability is, that means first you have to understand xi m. So your xi m is very greater than 1 or very greater than 0. Okay, so if it is greater than 0, then one, suppose we are taking it is as 2 equals to 1 minus mu r. So mu r equals to what? Mu r equals to negative, less than 0. Okay, mu r should be negative. So these are the values for ferromagnetic material. Okay, so right, when an external magnetic field is applied on the ferromagnetic material, when an external magnetic field is applied across the ferromagnetic material, then it will convert it into electromagnet. It will convert it into an electromagnet, or a magnet, okay, which will produce a constant or uniform magnetic field from north pole to south pole, okay. Okay, so this is for ferromagnetic material, and now your next topic will be this topic may be topic number 9, right? So next topic will be topic number 10. Next topic will be hysteresis on ferromagnetic material, okay, hysteresis on ferromagnetic material. Okay, so now next topic is topic number 10, hysteresis in ferromagnetic material. So what do you mean by hysteresis? First you have to learn and understand what do you mean by hysteresis, right? Hysteresis is a response. Hysteresis is a response of the ferromagnetic material. Hysteresis is the response of a ferromagnetic material under the experience of any external force, under the external applied of any experiencing of any external electric field or magnetic field, okay, external magnetic field, right? Okay, so that means whenever we are taking a ferromagnetic material, okay, so example of the ferromagnetic material I have forgotten to tell you that the example of the ferromagnetic material is your iron, right, Fe, okay, then cobalt, then nickel, okay, these are the examples of ferromagnetic material, Fe, cobalt, nickel, okay, and the best one is alnico, okay. Alnico is used to make any type of magnetic device, okay. So alnico means aluminium nickel cobalt mixture, okay, aluminium nickel cobalt mixture, okay. So suppose we are taking a material, ferromagnetic material, okay, and over it and which is placed inside any magnetic field, okay, then it will experience a magnetic force, and due to this magnetic force it can be enhance its magnetization, or it can magnetize itself, okay. So the response of the magnetization due to this applied external field is called the hysteresis, okay. So it's called the hysteresis. So first write down the hysteresis. So now hysteresis is a curve drawn by the response of B vector and H vector for any magnetic material, for any ferromagnetic material. That means you have to draw a BH curve, okay. So hysteresis is also called the BH curve of a ferromagnetic material, okay, of a ferromagnetic material. So now we have to draw this BH curve, then you have to discuss by me that the topic one by one, okay. So first let us draw it and then I will tell you, okay, one by one. So your result will be, so we have to apply a B vector and H vector over here, so it will be minus H vector and this axis will be minus B vector, okay. So a ferromagnetic material, when no external force is applied, that is when H equals to 0, that means at this point when H equals to 0, there also have some magnetic, so B naught is present inside the material. So this B naught, this amount of magnetic flux and magnetic flux density is called retentivity, okay, is called retentivity. Retentivity means due to retentivity, write one point one by one. I will discuss here and write, you have to write down the points one by one. So first write the point retentivity. Retentivity is is due to the residual magnetism. The residual magnetism present inside any ferromagnetic material. So retentivity is due to the residual magnetism present in any ferromagnetic material. That means residual magnetism means what? The magnetism which is inherently present in this material. Okay, inherently present in this material. Okay, so now next, if we increase the external magnetic applied force from 0 to positive value, then it will rise up to by this line. Okay, rising up to this line, and it will reach a maximum point. Okay, and now, so this is your maximum point. It will be your H max, whatever the maximum. So if we increase the H, it will never extend it. Okay, it will stop over here. So it will be your H max for any particular material. So H max will be constant for any particular material, and then if we decrease it up to a value, then it will back from the another line. Okay, it will back from the another line. Okay, and see, when the B equals to 0, then H cannot be equals, H never get a 0 value. That means when the H equals to 0, then B not equals to 0, and when after reaching the maximum point, if we apply the negative force gradually increasing, negative force is gradually increasing, that means it will coming from another path, coming by through the another path, and it will reach a point. This point is called your this point, suppose this will from A to B, B to C. Okay, and you have to, in order to make it 0, you have to apply another field. Okay, so this field, this amount of force is called, to make it forcefully you have to make a 0, and if H equals to 0, when H equals to 0, then it will produce a negative field. Okay, negative B. Okay, and then gradually it will C point, suppose it is your D point, and gradually it will reach the maximum. This is your H max and this is your H mean. Okay, and in order to make it 0, this amount of force DE F, so this OF is called coercive force, coercivity. Okay, coercivity is the amount of force required to forcefully make B equals to 0. The amount of negative field is required to forcefully make this residual magnetism be 0. So forcefully make the B equals to 0, that this amount of force is called the coercive force or coercivity. Okay, so retentivity will show OA line and coercive force will show OF line. Okay, so this loop is called hysteresis loop, and once it is magnetized and demagnetized, okay, here the magnetization is fully complete, and here the demagnetization is fully complete. Okay, and if we again reach in negative value, then it will actually reach its negative magnetization with refer of the applied magnetic field. Okay, that means the retentivity and coercivity, there are two terms for this hysteresis, and this curve is called also magnetization demagnetization curve, or this curve is called hysteresis or BH curve or magnetization demagnetization curve. Okay, so mag demag curve also can be treated as. Okay, so and the amount of area inscribed by this curve or by this loop is called your hysteresis loss. This is called hysteresis loss. Okay, what is hysteresis loss? Hysteresis loss is the amount of energy lost due to magnetization and demagnetization of any ferromagnetic material. Suppose I am considering a transformer core. This transformer core need to be magnetized once, and then it need to be demagnetized also. So this magnetization and demagnetization process needs little bit amount of energy. So this energy actually cannot be utilized by this transformer. Okay, so this amount of energy is lost by calculating the area of inscribed by this loop. Okay, so this is called your hysteresis loss. Okay, this is called hysteresis loss. Okay, so today's topic up to this much. Next day I will start the your class number 36, that is the last topic, the boundary condition of the magnetostatic field. Okay, so it will be the last topic. Okay, and after that class, after that topic, your this module is completed. Okay, okay, thank you.